try and do is explain to you what surface tension is. I'm going to try and tell you how it relates to intermolecular forces. Are there any chemists in the audience? Good, I think I've escaped the chemist. How about physicists? Okay, so I'll just warn you that I'm going to make some simplifying assumptions. I'll try not to say anything that is strictly wrong, but you're going to have to give me a break at some point. After we talked about intermolecular forces, I'll tell you why raindrops are spherical, which is different than the popular conception. I'm going to talk to you a little bit about designing a fuel tank in space, which has some interesting challenges. And finally, I'm going to tell you how detergents work. And then I'm going to give you a little snapshot of a two-dimensional fluid system, which I study with a group of physicists and chemical engineers. So let's get this started. We've all seen surface tension in acting on many places. But I want to concentrate just for the moment on a biological application. It turns out there's a whole set of organisms that live on the surface of a fluid. And they do things that you almost think shouldn't be possible. I mean, they walk on water. Okay? So at the top, we see a freshwater spider. At the bottom two are water striders. It turns out a buddy of mine, a guy named John Bush at MIT, who's actually in the math department, studies these organisms and how they sit on this interface. And the question is, okay, how can they do this? How is it possible that an insect can be supported by, I mean, why doesn't it just sink? I mean, if we tried to walk in a swimming pool, it would be rather calamitous. And the answer is that surface tension can easily support the weight of an insect. And I'm going to have you all demonstrate this to yourself. This is where the lab portion comes in. I'm wondering, is there someone here who can be my lovely assistant? So I want you, let's see. Stephanie, can I recruit you quickly? Or, okay. So everyone should get, I'm going to pass out some bottles of water here. Yeah, so in fact, can you folks come down and help me out here? Everyone should get a glass of, a plastic glass here. Okay. Yeah, it's fine to share, I'll say. And the other thing which you need are paper clips. So everybody should take a paper clip or two. Okay. So let's get these passed out. And we're going to do an experiment. Oh, and I forgot also. If you can. That having a tissue will also make this easier. Okay. I'm going to leave those with you, Heath.
Absolutely.
Okay. Okay. So here's what we're doing. This is just a normal Pyrex plate. I grabbed it out of my kitchen this morning. You have smaller experimental apparati. So you want to take the glass which you have and fill it up with water. There we go. I'm going to do something that's going to help me focus on the top here. This is just a pepper shaker. So a little bit of pepper on the top. And now I'm just going to take this and focus it here. So let's see. So you can see the pepper molecules. In the tray, this is what we call Lagrangian marker particles. Okay. And then what I want you to do is the following. We're going to float a paper clip on here, but it turns out this is much easier if you do the following. You take a little piece of a tissue, and you think of this as a raft. Okay. And then what you need to do is, okay, so that didn't quite work the way I wanted to. I'm going to do this again. You want your raft floating on the top, not sinking to the bottom. Okay. And then what you do is you take your paper clip and you very carefully put it down on top of the raft. Okay, that was an abject failure. I assure you this can be done. Okay. Oh, did I hear that somebody's got this working? Okay. It's all about the technique. Ah, okay. And then what you can do actually is, so that paper clip is actually floating. I'm going to now, carefully remove the raft, getting rid of the evidence. Okay, and there I have it. I have a paper clip that's floating up there. I'm going to do a little bit of focusing here. And I think you can see there it is. It's floating. Just out of curiosity, how many of you actually have a floating paper clip? Okay, you've all passed the surface tension exam. Okay, so you can sit there. That's going to be your little toy. We're going to come back to it later. One of the things I found fascinating, by the way, so if anyone wants to know a present to get me, apparently if you're in Japan, they have 1 yen coins that are small enough that they can be floated on the surface of a fluid. Okay, so here's a floating coin here. So what's going on here? Well, we've got this thing floating. Basically, surface tension somehow is pushing an upward force on this paper clip and supporting it. And what I want you to try and understand is how this relates to intermolecular forces. So the question is, what is the origin of surface tension forces? And the answer is that somehow this is related to the fact that the water is made up of a bunch of molecules, and those molecules are sticking together. That's the reason it's a fluid. Okay. So let's get into that in just a little bit more detail. Here's the part where the chemists need to just understand. I'm talking a little bit about bulk model. If I think about having just 2 molecules here, and I ask about the energy that's associated with having these molecules a distance d apart, the answer is the following. If I put them right next to each other, you get what's called polar repulsion. Basically, this is just saying 2 molecules can't occupy the same space at the same time. So the potential starts out very large. At intermediate distances, there's a dipole-dipole interaction. This is like having 2 magnets, and basically those 2 magnets attract each other. So these 2 molecules want to move together. If they get too close, the repulsion pushes them apart. And then if I'm further away, it pulls them together. So somewhere down here is the sweet spot, this equilibrium distance. And in fact, it's about 10 to the negative 10th meters. I'll point out, if I were actually to draw this diagram correctly, it has all sorts of little wiggles and bumps, which chemists have spent long amounts of time studying to get the details correct. But as a bulk model, that's right. Now, what does this mean? Well, the basic thing I want you to take home is you want to be close, but not too close. Okay. Sorry? Well, it sounds like marriage, but here's actually the example which I think about it is, okay, so Harvey Mudd has just won the football. I mean, we do actually have a football team, but they've just won the conference championship, and everybody rushes onto the field. So fluid molecules are basically like individuals in a crowd. You rush onto the field, you see this big crowd of people over here, you want to celebrate with them, you run up to them, and then you say, you know, I like these guys, but you know, I'm fairly comfortable just being about a distance here. Okay, so you know, there's this comfortable distance, and that's actually what molecules are doing. They're all running to the crowd. Now, again, there's vapor pressure, there's molecules that are going on and always constantly going off, but in the bulk, everybody's trying to run together, and that's the reason you get a fluid. And so when you see a fluid, I should say you should be thinking about is a crowd of people milling around, all interacting with each other, staying roughly the same distance away from each other. Okay, now, what does that have to do with normal forces? Well, the idea is the following. If I look at individual molecules, their ideal state is to be surrounded by as many other molecules attracting them, so they really want to be buried in the center of the fluid. But they can't all do this, but the ones on the outside are the ones that are the most unhappy because they have less neighbors. They feel less popular. So how can they become more popular? Well, the answer is they burrow into the fluid. And the way to put the least number of molecules on the outside is to flatten the surface. So the net effect of this intermolecular forces is that you want to flatten the surface. And the way you flatten the surface is that you evolve according to the curvature. So if you have a dimple inward, these molecules, if you push them outward, you actually minimize the area here. And if you have a dimple outward, if you push that down, that again minimizes the surface. So if you like, if you have a container, the molecules are most happy, the energy states the least if the surface is flat. And that's what's going on here. Now let's come back and interpret that in terms of the paperclip or a witter spider. Okay. Basically, what's happening is you have a solid, it's pushing down. And when that solid is pushing down, these molecules are saying, okay, I've deformed the surface. That's a lower energy state for me. I really want to push back up. And that's where the normal force comes. It supports this paperclip. Okay, and that's the origin of surface tension. Surface tension basically is a result of all these molecules wanting to stick together. Okay, well, what can we learn from that? Well, mathematicians think about problems like this. Suppose I have a surface, it has a fixed volume, and what I want to do is I want to minimize the surface area. This is a fact I think is fairly well known. We give it the fancy theorem of the isoperimetric theorem. What it turns out is that all the surfaces that minimize the energy, the sphere has the least surface area per unit volume. So given a droplet, it really wants to be spherical. And this brings us to the answer to our second question, which is the shape of raindrops. So there's a raindrop up at the top, as it's normally drawn. This is actually taken from a website called Bad Science, okay? Which for some reason, whenever I hear bad science, I think bad romance. I'm not sure why that is, but raindrops are not that shape. The general belief is that people see that shape, and it's because that's the shape that a raindrop running down a window pane takes. But in fact, here are pictures of actual raindrops. Here are some small ones, and small raindrops are perfectly spherical pretty much. Here are some larger ones. These are between 1 and 4 millimeters. What I want to point out is that as the raindrops get larger, because of wind resistance, wind shear as they go down, the bottom flattens. Something really interesting happens. They get to a width of about 4 millimeters, half a centimeter, I think. And you get a dimple on the bottom. And then there's this very sudden evolution. You get a dimple. It basically becomes a spherical shell, sort of a parachute shaped, and then it breaks up into a bunch of smaller droplets. And that's the reason that raindrops are limited in size to roughly about half a centimeter. Occasionally you see them larger than that, but really you see they are very small things. Now, this effect has to do with raindrops falling. It has to do with wind shear. So there are two ways to actually get rid of that limit. One is to do this in a vacuum, which has all sorts of other problems, but the other is to get rid of gravity. So I want to talk to you a little bit about getting rid of gravity. I want to talk to you about actually a set of experiments that a buddy of mine did. So here's a video from Science Friday. Can you hear that okay?
What would happen if you pop a water balloon in space? This. That's Seth Lichter, now a mechanical engineer at Northwestern University.
And big buddy of mine, I've known him for years.
He demonstrates some basic physics of how water behaves.
And I started thinking about, well, what would Galileo do to try to illustrate fundamental physics? And then it was just a fun factor.
And that's Mark Weisenthal, now a mechanical engineer at Portland State University. NASA's low-gravity aircraft simulates weightlessness by flying in a special parabola.
Basically trying to fly the path that a rock would fly if you just let it go. And then the plane did something like 60 of these parabolas with just one low gravity thing after another.
And that's a lot of stomach drops, Lichter says.
We go up, second cycle, I am sick as normal. It's a 12,000-foot high roller coaster. Every time going up. The beginning is gut-wrenching. Please stop me at any time. This is too much. My breakfast came up.
Yeah, that's too much.
I'll just tell you.
And it's euphoric.
And for you, Dr. Lichter?
Slightly better.
Part of the appeal of the water balloons is that they give you an easy way to make big water blobs on the spot with no fancy equipment. And that's because of the way that the balloon pops. You can see it here in these high-speed videos. When you pop a water balloon, even here on the ground, the first thing that happens is that the latex unwraps, leaving behind a big ball of water. On the ground, of course, that doesn't last long.
Only for a split second. Then gravity starts working on it, and the water blob starts to fall. And it takes that nice spherical shape
teardrop in space? Unlimited. For Science Friday, I'm Flora Lehman.
So I just want to say that I was at Northwestern when Seth actually did this experiment, and when he came back, he talked about it nonstop for months, okay? But the video is really quite amazing, and one of the things you realize is just how much gravity dominates the behavior of fluids in terrestrial environments. Okay, so now you know if you want bigger raindrops, got to go into space. Okay, so I want to talk to you about something that's also related. Here are some pictures of the top one on to the left is a fountain. This is a dripping faucet, and this is actually a very carefully run experiment of a very viscous fluid. And what I want to point out is that in all these cases, what you see is you see cylinders of fluid that break up into droplets. This is what's called the Rayleigh instability. And it turns out that surface tension is behind this instability also. This historically was studied in the late 18th century. It's sometimes also called the Rayleigh plateau instability. Plateau studied this theoretically. In experiments, he found that if you had a cylinder, it tended to break up into droplets that were about 6 times the radius. And Lord Rayleigh, who did an enormous amount of very important fluid mechanics, actually did a calculation and showed the breakup occurred at 2 pi times the radius. 2 pi, 6, about the right number. And I can explain this to you using these ideas from surface tension. So remember that if we look at the system, what is it trying to do? It's trying to minimize its surface area per unit volume. So I want you to think about taking a long cylinder, which has a certain surface area, and chopping it up into a bunch of shorter cylinders, and then turning them into spheres. And the question is, which has less surface area? The shorter cylinders, and by the way, you don't include the end caps because they would actually be pushed together, or the spheres. And you have a graph over here. And what you discover is that if you look at this, that for small spheres, the surface area is larger per unit volume. But as you go longer, in fact, the sphere has less surface area than the cylinder, the corresponding cylinder. So it's more efficient, it reduces the surface area to chop the cylinder up into a bunch of pieces and get spheres. Something that's really interesting is this is the energy argument. If there's anybody out there that studies dynamical systems, it turns out that in fact, the cylinder is stable up to a radius of 2 pi. There's a subcritical bifurcation here. And so that the crossover point, you can only get to this point by going above a length of 6 and going back. So that's a little technical, but the big thing you want to know is that what drives the Rayleigh instability is this idea that spheres are more efficient ways to package the wood or to reduce the surface area than cylinders are. And this results in some amazing dynamics. Let me show you again another experiment from John Bush. These are what are called fluid fishbones. So it's a little bit difficult to see the one on the left, but let me explain what's going on. I have 2 fountains of a very viscous fluid, and they're running together. And when they hit, they actually splay into a surface. And what's interesting is if the fluid are viscous enough, you see a link here, and then another link, and then another link. You get what's called a fluid chain. But if you turn up the flow rate a little bit, those links, those plates actually break up, and they make these amazing patterns. I think you can see why they're called fluid fish bones. It sort of does look like a fish in its bones here. But you see these droplets coming off here. This, in fact, is the Rayleigh instability in action. So if you look carefully, if we blow up the region in the green rectangle here, you see that you get a jet of fluid, and the end of the fluid breaks off into a sphere, and then you see another sphere breaks off here, and eventually breaks up into a bunch of droplets. Okay, so in fact, that's the Rayleigh instability encapsulated. Long cylinders of fluid break up into droplets. You see this in fountains all the time. If you want to see an experiment of this, I just suggest you go out and look in Hickson Court. Okay, so that's the Rayleigh instability. It turns out that another problem which I'm interested in has to do with wetting. So I'm going to actually go on from the Rayleigh instability here. Let's talk about the interactions of fluids and solids. Again, everything is all about energy. And it turns out that there are some solids, some materials, which fluids really like. The best example for that, I think, is probably oil and water. is that oil tends to spread out to be very thin. This is the whole idea of the Millikan oil drop. Then there's what's called partial wetting, where you actually get drops that sit there, which stick to the fluid in sort of a normal droplet shape. And finally, we see surfaces that are hydrophobic. This is a drop of fluid sitting on a leaf here. And I want to try and explain to you this again in terms of energy. So let's talk first about partial wetting, because the other two are extreme cases. Here's the idea. If I look at a drop on an interface, it actually has, there's three sorts of contacts here. We have a gas-fluid interface, we have a fluid-solid interface, and we have a gas-solid interface. And each of them has an energy per unit length associated with them. So I'm going to call those alpha for the gas liquid, beta for the solid liquid, and gamma for the gas solid. And this system's trying to minimize its energy. So what you can do, in fact, here's your homework problem for today, is go home, think about this being a cylindrical cap, a spherical cap of a particular radius. Write down the energy which is associated with these systems and minimize it. Okay, and what you discover is that you get a contact angle here. That is, if you look at the angle at the edge here and you write theta as the angle, the interface here, at the angle basically between the edge of the drop and the solid interface, you discover that cosine theta is equal to gamma minus beta over alpha. I'll explain a little bit more about that. Now, if you look at that, somebody says, well, there's some assumptions built in there. Cosine theta is between 1 and negative 1. So in fact, this tells me that this is the case as long as the magnitude of gamma minus beta is less than alpha. So if we look at that situation, what we see is the following. When that holds true, is we get these droplets, they hold spherical caps. Now, we can use this in terms of engineering certain things. This is Southern California. We all define ourselves in terms of our cars, and we want our cars to be nice and shiny. And for that to be the case, you want, well, if it rains, you know, it always rains in Southern California, and, is that you want the water just to sheet off and drop off. And the way you can do that is actually by waxing the car. What happens when you wax the car? What happens when you wax the car is that you decrease, you increase the energy cost per unit length of the interface between the car, the solid surface, and the fluid droplet. And since that becomes energetically more expensive, what happens is the contact angle becomes steeper and steeper and steeper. The droplet comes off. And because of that, the water flows off the car naturally, and it looks fabulous. Okay, so that's why we wax our cars. Now, there are two other extreme cases. It turns out that if alpha plus beta is greater than is less than gamma, what this means is the following, is that having a solid air interface is much more expensive than having a solid fluid interface. This is the case of complete wetting. So the fluid basically wants to stick to the interface. And in fact, there are two instances where you see this often. One, which is one which I use in experiments, which I'll explain about in a little bit, is when you put a drop of oil on the surface of water. It spreads out to be 1 molecule thick because that is energetically favorable. And this actually, again, is the way in which Millikan determined the size of a molecule originally. The second instance is when you cook something. One thing that's well known is that when you heat oil, the cost of a solid liquid interface goes down. That is the energy associated with that. It also turns out the cost of a liquid air interface goes down. Surface tension reduces. So heating things up tends to reduce these interface costs. And because if you pour a drop of oil into a frying pan, turn the frying pan on, turn the heat on, it spreads out to be a very, very thin layer. And this is great because it provides the lubrication layer between the food you're cooking and the solid pan. Okay. So cooking makes use of surface tension also. The last case is perhaps the least familiar, and that's when the cost of the solid-liquid interface is very expensive. And these fluids are called hydrophobic, water hating. By the way, hydrophobia is rabies. I love it. This crowd actually knows these trivia questions. Okay. So what happens is the fluid really wants to pull itself off the interface. There's some interesting ways of doing this. On the left, I have some manufactured examples. On the right, I have some biological examples. This sometimes is called the rose petal effect because, in fact, rose petals are hydrophobic surfaces. On the left, there are, I have 4 manufactured examples. The one on the top left I'll talk a little bit more about. This, in fact, is a hydrophobic salt, which has something called a fractal surface. This is basically somebody's model of this biological surface. And let me just talk about that in a little bit more detail. The 2 basic mechanisms for doing this, the biological one is what's usually called the lotus effect. Lotus leaves, it turns out, shed water very easily. And one of the things they feel is this is a biological adaptation to actually create a pool of fluid at the bottom of the leaf to nourish the leaf. And when you look at the surface of the leaf under a microscope, you discover that there are many, many tiny hairs sitting on the surface. So, so when the fluid comes down to the surface, if it tries to push into the surface, it has to contact all those little fibers. And that increases the energy cost for that fluid-solid interface. Well, it turns out engineers have figured out ways to use microfabrication to reproduce this effect. They use something called the fakir effect. So do you know what a fakir is? It's an Indian mystic who are known for lying on beds of nails, okay? And what's going on here is, if you look at this fluid droplet, is that if you push it down, if it wants to penetrate the pillars, what happens is that it has to wet the entire surface of the cylinder. So again, it becomes energetically favorable. So here's a picture of the fluid drop sitting on this manufactured surface. By the way, this is 100 microns here between the pillars. So you can think about this. If you try and push this fluid drop down, it has to wet a whole bunch of surface area there. That's energetically unfavorable. So it sits on top like the Indian mystic. Okay. Now, knowing that these surfaces have different characteristics leads to an interesting design question. So let's pretend we want to design a fuel tank for space. The question is, what would you do? So if you like, here's the fluid tank. Here is a channel which you want the fluid to flow into the combustion engine, into the rocket engine. Well, you can imagine making the walls wetting, but then you might think that the fluid would just adhere entirely to the surface of the tank. You can imagine making the walls hydrophobic, but then you might just get a drop of fluid floating in the center. Maybe you could do some combination of this. It turns out that this problem is even more complicated than you might imagine. So I've got another video here. This is from the space station. Here are 2 possible designs for the tanks. And you notice the one on the left, you get a coating of fluid on the outer edge, and you get a bunch of droplets floating around in the center. The one on the right, you just get the fluid coating the edge. The question is, what's between the 2 of them? This is, by the way, the interesting thing about being in 0G is we have these droplets here, they're bouncing around. There's no reason for them necessarily to combine with the fluid on the edge. This is bad in terms of fluid tank design. You don't want blobs of fluid flowing out there where you can't use them. So I'm going to run this again slowly, and here's what I want you to do. I want you to concentrate on the areas at the bottom of each of these tanks. So let's see if I can do this. Up. Okay, there we go. Did you see it? I'll do it one more time. What I'll point out is what happens if these tanks, they're slightly different shapes. And when you shake them slightly, it turns out the one on the left generates a jet up through the center. You get a cylinder of fluid, it breaks up into drops due to the Rayleigh instability. The one on the right has been engineered to damp out that mode of oscillation. So I'm going to do this again. I think the easiest way for me to do this is just go back to the slide. You see the jet? In one case it's quite severe, in the other case it's relatively minor, and that's what gives rise to these blobs floating around. So the Rayleigh instability actually plays a role in this problem. What's done at the moment is a whole bunch of different systems. Sometimes they use bladders, sometimes they pump various sorts of gases in to try and get the fuel out. But it's an interesting problem to consider. Okay, so I want to return to the experiments here. So at this point, I need to pass out some surfactants. Surfactants are things that are very useful. Let's see, I'll take my lovely assistant Heath here and give him.
Everybody gets a tube?
Everyone gets something. So there's some bottles of shampoo that I have stolen from various hotels from across the country. There is some various detergents. And all I want you to do is to do the following. I want you to take a drop of that and add it to your experiment. Hopefully your paper clips are still floating. And here I need to do something very careful. This is an experiment I only get to run once. Okay. So I'm putting more Lagrangian particles on the surface. I'm now going to focus on those pepper particles. Okay. And watch closely. This, by the way, is Dawn. Many years' experience suggests that Dawn is the best fluid for the best surfactant for this. So watch. Here we go. Watch what happens. Just takes one drop. Did you see that? Okay. So, and did you notice what just happened? So the paperclip sank. So let me tell you what's going on here. I added a drop of soap. It spread very quickly across the surface, pushing the pepper molecules out of the way, and then the paperclip sank. Okay. So let's see if we can try and understand what's going on there. Okay. By the way, are your paper clips sinking? Who has a sunk paper clip? Okay. Okay. Does anyone need more surfactant here? Yeah. So by the way, if you're thinking of reproducing this experiment, I don't usually endorse commercial products, but it turns out that for whatever reason, Dawn dishwashing soap works better than anything else, and that's what that bottle is. Okay, so, okay, so what happens here? I guess the experiments are still in progress here. Okay. So what happens when you add these detergents, which are in a class of materials, class of fluids known as surfactants, is they absorb to the surface. That's the reason that you saw all the pepper molecules being pushed, pepper particles being pushed out of the way. And they actually reduce the surface tension. So I have a little picture here. So what is a surfactant? It's a portmanteau word. It's a word that comes from surface active agent. Okay. So a surfactant is an additive to a fluid or fluid mixture that changes its surface properties. Generally, surfactants have are long molecules. They have a hydrophilic end and a hydrophobic end. They have a piece that wants to stick to the fluid and a piece that sticks out of the fluid. And what happens is they orient themselves on fluid interfaces. So for example, if you've got your washing machine and you've got a lovely shirt that has a droplet of oil or something on it, you want to remove it. What you do is you add your favorite surfactant, maybe it's Tide, okay, and the molecules orient themselves on the surface, and what they do is they reduce the surface energy for that fluid-fluid interface. And when they do that, what this means is that this droplet, which at first was really cementing itself onto the solid interface, your shirt, and didn't want to come away, so it was saying, oh, you know, this interface with the water, the surrounding water is really not that bad. And because of that, you can actually wash things away. So by reducing surface energy, that's how we clean our clothes. It's also how we clean our dishes. That's the reason we add detergents. It basically makes the things, the oils that are adhering to the dishes, come away a lot easier. And since it reduces the surface energy, that's the reason the paperclip sank, is that the energy which it was using to support the paperclip was suddenly reduced and said, hey, I'm just going to sink into this thing because that interfacial energy is suddenly a lot less. Okay, now I use the fact that surfactants spread out on the surface of a fluid in my research. So let me show you, just give you a snippet of the sort of things I investigate. So what you're looking at in the left-hand corner is a picture of a high-tech surfactant. It's octyl cyanobiphenol. We selected this substance because there's a lot of things about it that are easy to control. But this is actually imaging a layer that is, in some places it's 1 molecule thick, and in some places it's 3 molecule thick. So you pour the surfactant on, it basically becomes 1 molecule thick most places, but if you push it around, if you make the trough size smaller, it piles up into layers that are 3 molecules thick. The layers that are 3 molecules thick are white. The layers that are 1 molecule thick are black. Now, if you think about this, how do you image something that's 1 molecule thick? A single molecule, single layer of molecules does not reflect very much light. Well, the answer is quite interesting. There's the experimental apparatus in the background. By the way, that's Jacob Wintersmith, who did a lot of the numerical simulations I'm going to talk about, but also helped out with experiments. The lab is at my collaborator Elizabeth Mann's lab it's at Kent State. And what you do is, if you look, you see the 2 arms there in the experiment. The experiment's right in the center there, and you see those 2 arms that are at an angle. One of them contains a laser. It's shot down at an angle of 42 degrees. 42 degrees, if you remember from physics, is what is called the Brewster angle. And in the absence of anything on the surface, you would get total internal reflection. So the light would just go straight into the fluid. Nothing would get reflected off. But in fact, if you have a molecule on the surface, a certain amount of light gets scattered. And it turns out that enough of the light gets scattered, you can get enough contrast that if you have a CCD camera, you can actually image this 1 molecule thick or 3 molecule thick layer. So you get enough of a contrast there, you can see this. Now, what I want to show you is an experiment. So that's a platinum needle that's being run through this thing. I want to point out, you see these 3 molecule thick layers. You get these long, thin tethers, and you notice what happens to them. No Rayleigh instability. They get really, really long, but they don't break up. And that's the question which you were trying to answer, which is, when you look at these long tethers which are seen, can we understand why they don't break up? Well, how do you do something like this? Well, that's another whole seminar, but I want you to visualize modeling a 2D fluid sitting on a 3D fluid, lots of mathematics, some reductions, some dimensional analysis, some reductions. You solve some partial differential equations. It turns out you come up with a fabulous way of doing this numerically, and here's the result. So here's our numerical simulation of the experiment. There's a tether that actually gets 1,000 times longer than it is thick. Okay, and it's a fairly nice evolution. By the way, just to be clear, why do these domains become circular? And that's what these things are evolving to. It turns out this is something called line tension. It's the 2-dimensional equivalent of surface tension. Just in the same way that 3D fluids want to minimize this, the length, the size of their interfaces, these 3D domains, these domains are 3 molecules thick, the domains are 1 molecule thick, they want to minimize the interface length. There's actually an amount called there's this phenomenon known as line tension. It's 2D surface tension. When I saw these pictures, I said, man, it's surface tension, except in 2D, and it probably should be even easier to study. And we went a little bit further. This is a little dim, but I think you'll be able to see it. You see the blue line around the outside there? We actually digitized this photo as the initial condition. What we have there is the green line is our numerical simulation. The white is the experiment. I'd say we pretty much got it right. Okay. I'll tell you that there's a 1-parameter fit in here. The parameter is an interesting one. I have the experiments, which are a motion picture. I have the numerics, which are a motion picture, and you're determining the timescales in which these are 2 running. And it turns out that that timescale actually gives you the line tension. It tells you how strong the line tension is. Knowing the line tension tells you something about the interfacial energy. This is actually what the physicists want to know. They want to know the energy per unit length associated with this interface between these 2 domains. And we actually can determine that to within about 3%. We've gotten to the point where you give us some snapshots of an experimental solution. We've got a piece of software you can run into, and I can tell you the line tension. Not bad. Okay. I'm actually going to finish on time. what are the conclusions we can draw here? Well, basically, hopefully I've convinced you the surface tension is a fairly interesting phenomena. I'm hoping that you'll go out there and proselytize the fact that raindrops are actually spherical. Every time you see one of these teardrop shapes, you'll say, no, 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 that's bad science. I've given you a little bit of idea about interactions between hydrophilic and hydrophobic situations, understanding about that surface energy plays a critical role here. And finally, I've tried to explain to you a little bit about how detergents work and given you a peek of my own research. So let me thank you for your attention.